Zig is a powerful programming language that emphasizes safety, performance, and simplicity. Today, we're going to delve into testing in Zig, a fundamental practice to ensure your code runs correctly and efficiently. We will explore the built-in testing framework, what Zig Test does, and how to write effective tests that can help maintain the reliability of your applications. So far, we have learned about undefined behavior in programming, particularly in the Zig language, emphasizing its implications on performance and reliability. We explored various causes of undefined behavior, such as division by zero, out-of-bounds array access, using uninitialized variables, improper type casting, and race conditions in concurrent programming. Understanding these pitfalls and leveraging Zig's safety features such as compile time checks can significantly improve coding practices. Now we will cover the importance of testing in Zig and how to effectively apply it in your projects. Now let's take a look at a simple example of a function in Zig that adds two integers and includes a test case to verify its correctness. The code begins by importing Zig's standard library, which provides essential functionalities. We then define a public function named add, taking two integer parameters, a and b, and returning their sum. This straightforward implementation ensures that we can efficiently add any two integers. Next, we want to ensure that our add function works as intended, so we write a test case for it. In Zig, test cases are defined using the test keyword, and we name our test add function. Inside the test, we call the add function with the arguments 2 and 3, storing the result in a variable. We then use Zig's built-in assertion function, std testing expect, to check if the result equals 5. This testing mechanism provides instant feedback. If the assertion fails, we know that there is an issue with our function. This approach not only aids in maintaining code reliability, but also cultivates good testing practices that help catch errors early in the development cycle. Now let's see how we can implement a function that handles division while properly managing potential errors. The divide function takes two integers, the numerator and the denominator, and utilizes Zig's error handling mechanism. If the denominator is 0, it returns an error, specifically error division by 0, to signal that this operation cannot be performed. This demonstration is crucial as it highlights the importance of anticipating edge cases in your functions. Next, we will write a test case to evaluate the functionality of our divide function. The test begins by attempting to divide 10 by 2, which is a valid operation. If an error occurs during this operation, we catch it, print an error message, and exit the test gracefully. This not only ensures that unexpected errors don't cause the tests to fail abruptly, but also provides useful feedback for debugging. Moreover, we'll also test the scenario where division by 0 is attempted. Here, we expect the function to return the division by 0 error. By explicitly verifying both the successful and erroneous cases, we reinforce the reliability of our code in handling various scenarios effectively. This comprehensive testing strategy helps maintain the integrity of our application, ensuring robust error handling. Now let's take a look at how we can implement a user management system with the ability to authenticate users. We begin by defining a user structure that includes fields for the username and password. This encapsulation allows us to represent users in a straightforward manner while maintaining their associated data. Within the user structure, we define a method called authenticate that checks if the provided password matches the user's stored password. This is achieved using Zig's memory comparison function, ensuring efficient and safe operations. Next, we will write test cases to validate the user authentication functionality. The test case named user authentication creates an instance of user with a username and a predefined password. Here we utilize the std testing expect function to make assertions about the behavior of the authenticate method. The test confirms that calling authenticate with the correct password returns true, while calling it with an incorrect password results in a false outcome. This testing setup is essential as it not only verifies that our user structure works as intended, but it also helps ensure that components of our application interact correctly, promoting higher reliability in our user management processes. Now let's implement the following simple function and its corresponding test case. Here, we define a function called add that takes two integers as parameters and returns their sum. This is a straightforward implementation, making it easy to understand the fundamentals of function creation in Zig. Next, we will write a test case for our add function. It is essential to validate that the function behaves as expected, so we create a test labeled add function. Within this test, we call the add function with the values 2 and 3 and store the result. To verify that our function works correctly, we employ std testing expect, which checks if the result equals 5. If the test fails, Zig provides clear feedback, allowing us to quickly identify and address issues. Now let's see how we can benchmark the add function. In the benchmark section, we measure the performance by executing the add function 1,000,000 times using a loop. This benchmarking capability is vital for ensuring that performance remains optimal as we develop more complex applications, enabling us to catch inefficiencies before they become problematic. Now let's take a look at how we can implement a test for reading a file in Zig. In this example, we utilize Zig's std.fs file to open a file called testfile.txt for reading. We use error handling with the catch statement to gracefully manage the scenario where the file might not be found, avoiding abrupt test failures. Next, after successfully opening the file, we employ the defer keyword, which is crucial in resource management. By placing file close after the file opening, we ensure that the file will be closed automatically after the test case concludes, regardless of whether the test passes or fails. This practice prevents resource leaks and promotes clean code. Following this, we read the entire content of the file using read-to-end alloc, leveraging Zig's memory allocator. Again, we handle any potential reading errors. Finally, we assert that the file's content begins with the expected string using std, testing expect, providing a confirmation of the correct behavior. This structure not only ensures our test is thorough, but also showcases the importance of resource cleanup and error handling in testing scenarios. As we wrap up this lesson on testing in Zig, it's vital to remember the key message. Testing is not just a checkbox on your development process, but an integral part of building reliable software. By writing tests, you're investing in the long-term health of your codebase, making future changes safer and easier. We have covered a wide range of topics today, from writing simple tests for basic functions to more complex scenarios involving error handling and interactions between components. You also learned about the organization of test files and the significance of benchmarks and resource cleanup in ensuring tests run smoothly. As you continue your journey with Zig, keep in mind that adopting testing best practices will undoubtedly pay off, leading you to develop robust applications that stand the test of time. Thank you for joining me today, and happy coding.